Welcome to the second presentation in Unit 9 entitled Mangia, bene, vivi, felice. This is eat well and live happy, and it's an Italian proverb. So, the goals for this particular presentation are that you be able to dilute a solution to an appropriate molarity using a serial dilution procedure, that you be able to relate the change in colligative properties to intermolecular forces, and that you conceptually describe the factors that affect the solubility of a solute. So here's what we know. We know that solutions can vary depending on the concentration of the solute in the material. That's what we looked at in the last presentation. The idea of molarity and molality as being concentrations. We know that the higher the concentration, the more solute there is dissolved per volume. And we also know that polar solutes require polar solvents. So here's what we learned in the lab. According to adding salt to the solution can affect the boiling point. In fact, we saw that if you were to take them and graph them, you have grams of salt, and then you had boiling point. And you saw a steady increase that as you increased the grams of salt, it actually increased the boiling point. So the first thing we need to talk about is the idea of diluting a solution. You see this formula right here. It says M1V1 equals M2V2. Where this really comes from is the idea of looking at the solute. Whenever you have a dilution, what you're doing is you're taking a small amount of a concentrated solution and you're taking it into a larger volume, but you still have the same number of particles. So you're diluting it because the number of particles are the same. So really this comes from the idea that the number of moles of 1 equals the number of moles of 2. So you see this equation, it's M1V1 equals M2V2, where both M stand for the molarity and both volumes stand for the volume. So in this case, it actually does not matter what the units of volume are as long as they are the same. So if you want to put it in liters, great. If you want to put it in milliliters, great. The same thing is true for the molarities. As long as both molarities are in the same unit, this equation will work. Whether it's a molarity or a millimolarity or micromolarity or anything like that, as long as they're the same units, it won't matter. There's also a procedure called a serial dilution. A serial dilution is useful whenever you have to do a very, very large dilution. So in other words, you have something that's very concentrated and you need to make it very dilute. So what you do is instead of taking a small sample and adding a whole bunch of solvent to it, you add and you dilute it by a factor of 10 each time. So in this case, you can take and you can add 1 ml. This one actually shows us diluting by a factor of 100 each time. But what we're doing is we take a small sample of the very concentrated and we dilute that to usually something around the order of 10 mils. Then we take a sample of the diluted and we dilute it again. And we take a sample of that diluted and we dilute it again. And we keep diluting it over and over and over again until we get the dilution that we want. Now, the reason for a serial dilution is that it has greater accuracy and is less wasteful of material. So in this says it says which one of these represents the diluted solution. Now remember, diluted is the opposite of concentrated. So this one is the most concentrated, which means this one is the most dilute. It says the student needs to dilute a stock concentration of 15.8 molar hydrochloric acid to 0.1 molar. The student determines that she will need 250 mils. What is the amount of stock solution the student can use to get the solution she needs? So this is what she needs, 0.1 molarity, 250 mils. This is what she has. So we need to dilute the 15.8 molar hydrochloric acid to 0.1. So we know the number of moles are going to be the same. So we can use the formula M1V1 equals M2V2. So M1 is 15.8. M2 is 0.1. V1, I don't know, and V2 is 250 mils. Now, it doesn't matter what units I use as long as they're consistent. These two units are the same. This unit is milliliters, which means my answer will be in milliliters as well. So, 15.8 times V1 equals 0.1 times 250. So now at this point you get your calculator out, you multiply 250 times 0.1, and then take that value and divide it by 15.8. And when you do that, you end up with a volume of roughly 1.6 milliliters. Now, this is a very, very big dilution. In order to be more accurate, it would be better to do the serial dilution procedure. Now, colligative properties. Colligative properties are properties that change based on the ratio of the solute to the solvent. So, for example, it's going to change based on the concentration. So, if you have 1 mole per liter versus if you have 10 moles per liter. So, these right here have different amounts of solute per solvent ratio. So in other words, the concentration is different. So the properties that change as a result of the concentration being different are what we call colligative properties. Freezing point is an example of a colligative property. It says the partial positive hydrogen atoms are attracted to the partially negative oxygen atoms. So you see different water molecules that they're attracted to one another. These two are attracted. These two are attracted to different parts of the molecules. So the reason why freezing point is considered to be a colligative property is as you add solute to something, you're actually increasing the attraction between the solute and the water as opposed to water and water. So the attraction between this negatively charged ion and the water is greater than the attraction between water and water. Because of that, we can say that the boiling point is affected by what we call intermolecular forces. Those are the attraction between different molecules. So it says cations are full positive charge, anions are full negative charges, as opposed to the partial positives of oxygen. Next, you have the idea of freezing point. Freezing point depression. Your engine does not freeze when it's icy outside because you add a solute to it to change the freezing point of water. Generally, we use something called antifreeze. Antifreeze is usually ethylene glycol and water mixed together, but what you see is you can do something just as easily with salt. Whenever you take and you add salt to water, it will actually decrease the freezing point. Here's an example. If you have 10 molality solution versus no molality, you can drop the temperature of the water from freezing at 0 to freezing at -20. Once again, the reason for it has to do with the idea of boiling point is also a colligative property, and it has to do with the intermolecular attractions. So once again, whenever you put something that's in between here, that's a full positive or full negative charge, it will affect the intermolecular forces and it will affect the energy required to break these attractions. So once again, boiling point and freezing point are examples of colligative properties. So whenever you add a solute to intermolecular forces, the solute, such as sodium chloride, interferes with these intermolecular forces. The attraction between the fully charged sodium ion is greater than the partially charged hydrogen ion in water. You see boiling point elevation. The boiling point changes as the solute is added. How can you speed up the process of boiling pasta? Well, what you do is you add salt, and whenever you add salt, you change the temperature at which the water boils. So the noodles, instead of being exposed to 100 degrees Celsius temperature, they're exposed to 110 degrees Celsius water. Well, at 110 degrees Celsius, they're going to cook faster than they would at 100 degrees Celsius. Next, we need to talk about the solubility of a substance. We've already talked about it to some degree. It's the amount of solute that can be dissolved. But generally, when we refer to something by the solubility, we're talking about whether it will dissolve at all instead of how much dissolves, like we talk about with molarity. So whenever you have something that's called an unsaturated solution, what you're saying is that solution could take more particles. So for example, if you take 1 scoop of Kool-Aid powder and put it in water, you get an unsaturated solution. You could actually put more in and dissolve more in without it crystallizing, but at that point it's considered to be an unsaturated solution. A saturated solution is at the maximum level. So for that temperature, you have dissolved as much particles in the solution as you could. And then you finally have a supersaturated solution. A supersaturated solution is actually above the maximum value. And whenever you have above the maximum value, what you've done is you've created a solution that's either heated or the parameters of the solution have changed, or you actually have more dissolved in the solution than you really should. And what's interesting about a supersaturated solution is that if you were to give a supersaturated solution a seed crystal or something along those lines, the solution will crystallize like you see here. So supersaturated solutions are things that are used to make like rock candy, or if you've ever grown crystals at home, you have examples of supersaturated solutions. So there are factors that affect the solubility of a substance, and there are number 1, temperature, number 2, pressure, and number 3, the nature of the solute or solvent. So you have the idea of the temperature, the pressure, and what the nature of the solute-solvent relation is. So for a solid solute, the solubility increases as temperature increases. So the solids can't be compressed, so pressure has no effect. So really, if you're trying to dissolve something like sugar in water, really what you can do is you can increase the temperature of the sugar, and that will allow you to dissolve more. That becomes particularly important when you have things like Jello. Whenever you make Jello, you're told to boil the water first and then add the gelatin mix beforehand, and then you're just going to put it in the refrigerator. So the reason why that you bring it to a boil first is you bring it to a boil to dissolve as much gelatin in there as you can. Then when you put it in the refrigerator, it allows it to solidify. Now, since solids cannot be compressed, pressure has no effect. So if you were trying to squeeze a solution down somehow and press it in, it has no effect on how much solid you can dissolve. Gas is a little bit different. The solubility of a gas decreases as temperature increases. And the reason why is, as you increase the temperature, what you're doing is you're giving more energy to the gas, and the gas can escape the Coke bottle. Okay, so that's the first one. So for solids, increasing the temperature allows you to dissolve more. For gases, increasing the temperature allows you to do less. So if you want to keep more gas in there, you actually have to decrease the temperature. And that's why we tend to store sodas in the refrigerator. And finally, increasing the pressure does increase the solubility. So if you were to keep these sodas are generally stored under pressure. And you know that because whenever you twist the cap open, you can hear a noise. And that noise is the gas that's escaping, because the solution was originally stored under pressure. And this one, it says a salt solution is used to store salt. The solution is confined to a fixed container. What can be done to increase the salt in the container? And really the only thing you can do at this point is you can actually increase the temperature. And the reason why is salt is considered to be a solid. Because it's a solid, you can't compress it, you can't squeeze it, you can't increase the pressure in order to dissolve more. It's a defined substance, so since it's a defined substance, we can't alter the solute-solvent relationship. So really all you could do is increase the temperature. Finally, it says which of these substances is likely to be a gas, and if you look, we see temperature and we see solubility. And so the ones that we would expect to be a gas would be the ones that decrease as the temperature increases.